Hi, guys. Okay, so let's look at the exercise problems from Chapter 7, Chemical Reactions. And the book we are using is the book by Naval Tro. This is the Introductory Chemistry. And this book is available on the Libre text website. So the Chapter 7 from the Libre text website, the exercise problems are 7.21 and the problems in every section. So the first one is, which of the following is a chemical reaction? Chemical reaction is obviously involving either the evolution of, heat or the absorption of heat, formation of a solid, formation of a gas, maybe a color change, and a new substance is always formed. And there are certain, common terminology that is associated with chemical reactions in general. For example, rusting is a chemical reaction. It is happening in nature. So rusting is basically iron reacting with oxygen. Okay, so that's one piece. But if you look at some of the other things like painting, you're applying the paint on a wall, but you're just sticking it, but there's no chemical reaction happening. Similarly, when you're melting things is just a phase change, taking some things from a solid to a liquid, and that is, melting. It's just the chemical composition doesn't change. The chemical composition remains the same. Now, the chemical composition is not changing. That means it's just a temporary change. You can convert the melted substance into a liquid form back into the solid state, and the chemical properties are not changing. They will remain the same. Next is scratching. Scratching is just removing, the top layer, or, just scratching, like something. So scratching is also just temporarily, you are just breaking into small parts, but that just, it doesn't create a new substance. Scratching, okay? Making a sandcastle. So you're making something out of something, so it is still a sand. Okay, it is, although you created a new substance, which is a new structure, a new entity, but it doesn't, it's the composition, it is made up of sand. That sand is a chemical composition which remains the same. Okay, next is, which is not a chemical reaction. Now here, if you look at it, when you fry things, let's look at it. Frying is obviously heating things in oil at a very high temperature. A new substance is produced. Similarly, when you are dropping a fizzing tablet in water, like Alka-Seltzer in water, it releases carbon dioxide. Formation of gas bubbles, formation of a gas is a chemical reaction. So this is a chemical reaction. Next is creating ATP in the body. This is a biochemical change, biochemical reaction happening in the body. Now, falling, if something is falling from down from the top or anywhere, or if you're slicing is making, big parts, and you just made it into small parts, the chemical composition remains unaltered. Similarly, falling just changes the placement of a substance from one point A to a point B, but it doesn't change the chemical nature of a substance. So those two are, the no chemical reactions. The rest of them are. Okay, next, hydrogen fluoride gas reacts with the aqueous solution of potassium carbonate to produce an aqueous solution of potassium fluoride, liquid water, and a gaseous carbon dioxide. Transfer this information in symbolic equations. Now, when we talk about symbolic, chemistry is a language of atoms and molecules. Okay, so we use symbols there. And a lot of, in science, it's all symbols. So let's look at this here. So the important thing here for you is you need to memorize symbols from the periodic table and polyatomic ions, and you should know their placement and the charges. Okay, so all this I have created a quiz, a worksheet now. So you need to focus on that and try to learn, the things and memorize them. Okay. Now, hydrogen fluoride gas. Hydrogen fluoride is so hydrogen fluoride is HF. And this is how you write HF. So why it is it? Because hydrogen, group 1A, remember? And fluorine, fluoride is group 7A. So plus and minus charge cancel out. This would be the formula. Hydrogen fluoride reacts with, so it is a reactant, with aqueous solution of potassium carbonate. So potassium carbonate, and it is aqueous solution. So potassium group 1A plus 1 charge, and carbonate is the formula for the carbonate is CO3 minus 2. So this is known, like it's a polyatomic ion. So remember, crisscross, and they are going to produce K2CO3. Now it is saying aqueous. It's soluble in water, so it is aqueous. Okay, to produce an aqueous solution of potassium fluoride, and it is also an aqueous solution to produce. Now that means you're going to put an arrow to show that you're producing. Now here, it's a rearrangement in chemical reactions. So here you have potassium fluoride. Okay, fluoride is -1. So plus minus cancel out. You have KF, and this is aqueous solution, means aqueous. You write it like that. And next is the liquid and liquid water and gaseous carbon dioxide are produced. Okay, so liquid water is H2O. Okay, and liquid is shown like that, and gaseous carbon dioxide. So carbon dioxide gas, like that. So you write this down like that. So at this point, I'm going to make sure that this is, you understand that this is unbalanced. So because the question is only asking you whether, you can write things in the symbolic form or not. It's only testing you for that. Okay, so it's just, but right now it's not balanced. So you just write it. So you see one side are the reactants. These are the reactants, and this side are the products. Okay, and right now it's an unbalanced equation. Okay, next, transfer the symbolic equation into words. So here they are asking you whether can you write this in the word? Can you write down the names of the chemical compounds? So here you have HCl. HCl stands for hydrochloric. Can you recognize the formulas and their names? So hydrochloric acid. So again, this is going to be your nomenclature. Okay, hydrochloric acid, aqueous solution, AQUEOUS, aqueous solution. Aqueous solution means it is in water. Okay, aqueous solution, hydrochloric acid, aqueous solution reacts with what? Now, next, can you understand LiOH? LiOH is lithium hydroxide. Okay, so you should be able to write the names and the formulas. Okay, hydroxide. And again, lithium hydroxide is also aqueous solution. Aqueous solution means, aqueous solution literally means in water. Okay, in water, soluble in water. Okay, in water. Reacts with to give, what is it giving? Lithium chloride, lithium chloride. Okay, and then lithium chloride is what? It is also soluble in lithium chloride. Aqueous solution, AQUEOUS. Aqueous solution means the solution soluble like a lithium chloride in water. Okay, so this is all in water. Aqueous itself means that. And to give lithium chloride and water in liquid state, because water can be produced in vaporized state also, which is the gaseous state. Okay, in liquid state. Okay, so this is the way you write them down. Okay, so that's one piece. But generally, I'm not going to give you these, you write it, but as far as you understand. Okay, now here you are given this and they are asking you to balance. Okay, now this is an important one. Balance this. Now, anytime you have a combustion reaction, this is a balance. This is a combustion reaction. Combustion means reaction with combustion. Combustion means whenever lots of carbon-hydrogen bonds, okay, or any of them, any other things also, combustion always means reaction with oxygen, O2, okay? And so in this case, anytime lots of carbon and hydrogen bonds, no matter what it is, these are called organic molecules. Whenever organic molecules react, they are all going with when they are burnt in oxygen, they are going to give carbon dioxide, all of them, it's standard thing, plus water. And of course, massive amount of heat is produced. So a little bit of heat is given, more heat is being produced. So that's combustion, flammable reactions. Okay, so these are organic ones. Now we have a scenario C8H18. So in this case, always, so there is a rule here. First, balance carbon. Second, balance. So I keep writing balance. I'm going to do this here. First, then second, balance hydrogen. Okay. Last, balance oxygen. If there are odd number of oxygens, if there are odd oxygen atoms on the product side, so what do? Then multiply all species with 2. Then balance oxygen. Okay, so in case of that, oxygen is odd. So in this case, oxygen turns out to be odd. So that's why we have to do this. So these are some of the rules, right? So these are just the rules. So I'm going to just put this here and we will follow these rules and then you're good. Okay. Oh, what happened here? Sorry, just give me 1 minute. Okay, so let's do this now. So we have to write this equation. So here, C8H18 plus O2 gives you CO2 plus H2O. Okay, now here, let's write down what is given. So we are given 8 carbons, 18 hydrogens, 2 oxygens, 1 carbon, 2 oxygens, 2 hydrogens, and 1 oxygen. So we have 8 carbons here and only 1 carbon here, not balanced. 18 hydrogens, and we have only 2, not balanced. So let's focus on these guys first. So let's put here 8 carbon. So if we put 8 here, that means this 8 applies to carbon. This 8 also applies to oxygens. So 8 times 1 carbon and 8 times 2 oxygens now makes 8 to the 16 oxygens. Okay, and you have 8 times 1 carbon is 8 carbons. Okay, that's one piece. Next is, so carbons got balanced. Now let's look at hydrogen. There are 18 hydrogens on one side and there are 2. So how can you make them 18? So you are going to 18. So 9 2s are 18. So if you put 9 here, this 9 applies to hydrogen. This 9 applies to oxygen. So 9 times 2 hydrogens and 9 times 1 oxygen. So you have 9 2s are 18 hydrogens and you have 9 oxygens. Okay, so that way, now you see that the hydrogens 18 and hydrogen is 18. Okay, so carbons got balanced, 8 carbons, and the hydrogens got balanced. Now, let me put this also here, 8 carbons. So carbons got balanced, the hydrogens got balanced, 18 and 18 and 8 and 8. But oxygens is messed up. So let's look at the total oxygens. Total oxygens are, so we have 16 oxygens on one side, plus we have 9 oxygens on the other side. So how much is that? So 16 and 9 is how much? 16 and 9, 16 plus 9 is 25. So 25 oxygens on one side. So remember, this is an odd number of oxygens. Okay, so what will you do? Therefore, multiply others by 2. Okay, so we will have to rewrite this whole thing so I can Okay. Now, let me just copy this C8. So this is the next one now, next round. So this is part, so this is the first step, and this is the second step. First step, you do this. And in the second step, you do this. So 2, multiply by 2, right? Multiply by 2. 2 C8 at H18 plus leave O2 as it, don't touch it. Then gives you 2 times 8. 2 times 8 is 8 twos are 16. So 16 carbon dioxide, and then 2 times 9 is 18. 18 H2O. Okay, so we have now 18 and 16 CO2. Okay, now what are we doing here? We are going to check one more time. How many? 2 times 6, 2 6 are 2 8 are 16. So there are let me write this here. 2 times 8 carbons is equal to 16 carbons. 2 18 twos are 36. 2 times 18 hydrogens. So there are 36 hydrogens. Okay, and then you have 16 carbons, right? And then you have 16 times 2 oxygens, and that gives you 16 twos are 32 oxygens. And you have 18 twos are 2 is a 16, 30. So 18 times 2 hydrogen, and then 36 hydrogens. And you have 18. So 18 times 1 oxygen is equal to 18 oxygens. So you see here what is balanced. 16 carbons and 16 carbons are balanced. And then you have 36 hydrogen and 36 hydrogens balanced. So what is not balanced is the oxygen. So there are 32 oxygens here and 16 oxygens here. A total of 32 plus 16 gives you 48. Just 1 second. Okay, so 32 plus 18, 50. So there are 50 oxygens on one side. So how can you make 50 on the other side? You can put 50 oxygens here. You can make 50 oxygen here if you put 25. So 25 times 2 oxygens give you 50 oxygens. Okay, so that balances the oxygens also. So 50 oxygens here, 50 oxygens here. Okay, so this is how you balance these reactions that are combustion reactions. Okay, and balancing requires that. So just pay attention to odd electrons on the, and then how you are going to proceed with that. Okay, next is you're going to check whether this reaction is balanced or not. So how are we going to do this? We're going to write down, remember that this 3 applies to oxygen and this applies to the nitrate as a whole. So let's put this here. So this 2 outside is for nitrate as a whole. So this 2 applies to all of this nitrate, okay, as a whole. And this is 1 nitrate. So it's very important you recognize the polyatomic ions. So these are 2 nitrates here. There is 1 nitrate here. So what is not balanced? So if the question is asking whether it's balanced or not. So if you look at it, you have 1 magnesium, you have 2 nitrates, NO3. So when you're balancing, it's okay to leave out the charges in the beginning. Right? Ideally, once you get the hang of it, then you're okay. But, I don't want you to be lost with the charges. So here is this 2 nitrates, 1 magnesium. Here there are 2 lithiums. All right. Here there is 1 magnesium. And here you have 2 lithiums. And you have this, remember, this 2 applies to lithium. This 2 applies to nitrate also. So 2 lithiums and 2 nitrates. So what is not balanced here? So we see that we have two nitrates on one side and we have two nitrates on the other side. So those are balanced. Then we have two lithiums on one side and we have two lithiums on one side and we have two lithiums on the other side. So that is also balanced. Then we have one magnesium here and you have one magnesium here. So this looks like a balanced equation. Okay, balanced. Everything is balanced. Okay. So don't get confused, with the charge on magnesium. Sometimes it's okay. Next is this guy, which one is balanced and which one is not balanced. So there are two carbons, excuse me, and then there are, four hydrogens. Okay. Then you have 2 times 2. So 2 times 2 oxygens makes it 4 oxygens. Okay. There are 2 carbons, 2 times 2 oxygens is equal to 4 oxygens. There are 2 times 2 hydrogens, that makes it 4 hydrogens. There are 2 times 1 oxygen, and that is 2 oxygens. Okay. Now we have 2 carbons. We have 2 carbons and 2 carbons balanced, 4 hydrogens, balanced, 4 oxygens, and then remember there is 2 more oxygens. So 2, so here you have 4 oxygens and you have 2. So 4 oxygens plus 2 oxygens give you 6 oxygens. Okay, so this is 4 oxygens here. So oxygens not balanced. Okay, so this is very important. You see all, check them. So oxygen is not balanced. All right. Now we are going to look at so this is what it is. Next is we are going to look at the balancing. Now here's something. For some reactions, if you recognize the polyatomic ions, it's good to leave them intact. So don't break up into parts. So here you have 2 nitrates. Here you have 3 nitrates. So it's kind of obvious that they are not balanced. The rest of it, let's write this down. So we have 1 lead. We have 2 nitrates, NO3. So here I'm going to write down, it's okay to not put charges when balancing, when in the beginning, because sometimes ideally you should, but all that comes with practice. Okay, so for the beginners, it's fine. All right, then you have 2 nitrates, then you have 1 iron, right? And then you have 3 chlorines, 3 Cl, 3 chlorines. Okay, you have 1 iron here and you have 3 nitrates, NO3. You have 1 lead and 2 Cl2s. Okay, now let's see what is not balanced. So obviously 2 nitrates and 3 nitrates, those are not balanced. And anytime you have 2 and 3, we have to look at the common multiple. Next thing that is not balanced is the leads are fine. 1 lead and 1 lead is fine. The chlorines, look at the chlorines. So here is 3 chlorine and there is 2 chlorine. So these are not balanced, but iron and iron is balanced. Regardless, these are going to, even though they are balanced now, once you start moving, then everything becomes imbalanced. So what do we do? Okay, so we have 2 nitrates on one side, we have 3 nitrates on one. So we'll have to look for the common multiples, and then the chlorines are also 3 and 2. So we have to look for common multiples here. So if you put 2 here, so 2 times iron and 2 times chlorine, and we will have to go back and forth if we need to. So this makes it 2 irons and this makes it 6 chlorines. So how can you make the 6 chlorines on the other side? You're going to put 3 here. So this 3, remember, this applies to iron, this applies to chlorine. Similarly, this coefficient applies to iron, this applies to chlorine. So what do you get here? So 2 times iron, so 2 times lead and 2 times 2 chlorines. And this gives you 2 lead and 4 chlorines. Okay. Oh, sorry. 2 3s are 6 chlorines. Sorry. 6 chlorines. 6 chlorine. Okay. So what am I doing here? I'm sorry. I think I made a mistake here. this was 3, not 2. So that's why. Okay. 3 lead and 3. So this becomes 3 lead and 3 2s are 6 chlorines. Okay. So now we see here that the chlorine is 6 chlorine and 6 chlorine. These get balanced. So we have now iron to take care of, and we have the nitrates to take care of. So let's see. Here we are applying the nitrates to 2 nitrates and 3. Yeah. So see, this balances the lead. This makes them this 2 times 2, 2. So this makes 2 leads, and this makes 6 nitrates. Okay. And here you have 3 leads and nitrates now, 2. So times 2 times 2. So this is going to give you, sorry, let me just do it the other way. Okay. All right. So this 2 applies to nitrate and this 2 applies to iron. So 2 iron and 2 nitrate. So this gives you 2 Fe and 6 nitrate, NO3. Okay. So we see here 6 nitrates and 6 nitrates. Next is the chlorines were balanced. Chlorines are balanced. Next, look at the iron. Look at the lead. 2 lead and 2. Sorry. Oh my God, I am. Looks like I'm exhausted or what? This was 3. 2 3s are, yeah. I'm writing something and I'm so 3. Sorry about that. So 3 lead. I think I'm just rushing here. Okay, 3 lead here. 6 nitrates and 6 nitrates. 2 irons and 2 irons, and 6 chlorines and 6 chlorines. All this balances out. Okay. Sorry, I guess I was rushing a little bit. So anyway, so this balances the lead, 3 lead, 6 nitrates, 6 nitrates, 2 irons, 2 irons, 6 chlorines, 6 chlorines. Balanced. So always look for the common multiple when you have like 2 times 3 or 3 times 2 is equal to 6. So that was the deal over here. And it's okay to, balance and keep, another thing, keep polyatomic ions intact if they are the same. If polyatomic ions are the same on both the sides. Polyatomic ions are same in the reactants and product side. Okay. All right. So that's one thing. Next is you are also, so this question, this problem was also in the 7.9.3. Okay. So let's do this. Same thing. This problem was same. This problem was same in that chapter. So let's do this in the last section. Same story here also. We are going to first balance carbon. Second step, balance hydrogen. If oxygens are odd number, then multiply others by 2. Okay, multiply others by 2. After that, what? When you're multiplying other by 2, then last balance oxygen. Okay, so this is the strategy here. All right, let's do this. So we have C6H14 plus O2 gives you CO2 plus H2O. All right, and of course, this is a combustion reaction. So let's write down. There are 6 carbons. There are 14 hydrogens. Okay, and there are 2 oxygens. There is 1 carbon. There are 2 oxygens. There are 2 hydrogens, 1 oxygen. Okay, so now what are we doing here? we are going to see carbon is not balanced, right? So if you put, if you put 6 here, 6, this 6 applies to carbon and this applies to oxygen. So 6 times 1 carbon and 6 times 2 oxygens. So that makes 6 carbons balanced and 6 2s are 12 oxygens. So hold on to oxygens. Okay, next balance hydrogen. Hydrogen is 14 hydrogens on one side. You can make them 14 if you put 7 here. 7 times 2 is 14, but that changes the oxygen also. So 2 times 7 and 2 times 1 times 7. So this becomes 7 2s are 14 hydrogens, balances that, and oxygens. So 12 oxygens plus 7 oxygen is how much? 12, 17. So this becomes 19 oxygens. So that is an odd number of oxygen atoms. So what are we going to do? We are going to multiply others by 2. So for that, I have to rewrite the equation. Okay, so once again, up till that point. So once again, this is C6, H14 plus something on the O2. This gives you 6 CO2 plus 7 H2O. So this whole thing you multiply by 2. Leave this, not this. Okay, so this gives you now another equation which looks like this. So 2 C6, 2 C6, right? H14, 2C6H14. Let's do this here. So 2C6H14 plus, leave the oxygen, gives you 2 6s are 12 CO2 plus 2 7s are 14 H2O. All right. So now let's look at what we have. We have 6 2s are 12 carbons. We have 2 times 14, 28 hydrogens. We have 12 carbons, 12 times 2, 24 oxygens, right? And then we have what? 14 times 2, 28, 4 2s are 8, 14 2s are 28 hydrogens, and we have 14 oxygens. Okay, so check. Carbons are 12 on both the sides, and we have hydrogens 28 and hydrogens 28, same on both the sides. Now count 24 plus 14, 24 plus 14, and that is 38, right? That is 38 oxygens. Now 38 divided by 2 is what? 19. So that means that 2 oxygens, when you multiply it by 19, that is going to give you 38 oxygens. So the number here is 38. Okay. Oh, sorry, not 38, 19. 19. And that is the answer. Okay. So that matches the oxygens, 38 and 38. All right. All right, let's look at the next one, soluble or insoluble. Now this relates to the solubility rules. Now you guys have in your handout, I have given, hold on, we would need this. We would need in your handout. Okay, I have given you in your handout the solubility rules. Okay, these solubility rules are present here. Okay, now these solubility rules, keep these in mind that there are some exceptions, and the exceptions are they could be soluble, slightly soluble, sparingly soluble. And also there's another thing with the solubility. You can also, increase the temperature or decrease the temperature a little bit. You can fiddle out with that, and the solubility can increase or decrease. You can stir things. So solubility is kind of like, it can be varied. However, these are still some big, very broad, outlines which determine the solubility of some of the ionic compounds. So here you have sodium, potassium, all the group 1A elements and the ammoniums. These are soluble in water all the time. Anytime nitrate attaches to anything, anytime nitrate attaches to anything, it is always going to be soluble. It will always make it soluble. Same is the case, perchlorates. Anytime perchlorates attached to anything, that will become soluble. Then comes the fluoride. Anytime fluorides attach to any of the metal, they will be soluble except by anything. I mean the metal. We're talking about the ionic compounds, except the exceptions are, now here's an exception you guys should see, and I'm going to write here that Castro bar. Castro, so I don't know if I can write this here with red. Castro, C-A-S-T-R-O-B-A-R. Where is the bar present? It's present in the mol. Okay, so what is the meaning of this? This means, let's see, this means Castro. Castro means calcium. Stro stands for strontium. Bar, Ba stands for barium. Mol, M stands for mercury, A stands for silver, and L stands for lead. And these are the troublemakers. These are the ones that form the exceptions. They never fall. So you can see here, calcium, strontium, barium, lead, right? And mercury, again, lead, mercury, silver, right? Lead, silver, mercury, silver, mercury, barium. So these are the common ones, lead, strontium. These are the common ones. Anytime in calcium, these guys will have issues with solubility, right? They could be soluble, but partially soluble or sparingly soluble. It doesn't matter. Even if they're sparingly soluble, some of it is still insoluble. So we will just consider themselves insoluble. Okay, so keep this in mind that all the chlorides, bromides, and iodides are soluble, except barium, strontium, calcium, mercury, lead, and silver, mercury, lead. Okay. And fluoride, magnesium fluoride, I don't know why. Magnesium fluoride is also insoluble. And then also the copper iodide is insoluble, so these are, so you need to just look at this table and go from there. But at least from your memory, Castro bar in the mol means barium, strontium, calcium, and mercury, silver, and lead are always going to be like either completely insoluble or partially insoluble, but it will be insoluble. Okay. So for the question, if the question is asking, is it soluble or insoluble, we'll just consider them as insoluble. Okay. Next is the sulfate. All the sulfates where is that? Yeah. All the sulfates are soluble except barium, strontium, calcium, silver sulfate, lead sulfate, mercury sulfate. You see that? All of them are here. Acetates. All the acetates are soluble except the silver and like mercury acetate. Next are the insoluble ones. Which ones are insoluble? Insolubles are all the carbonate, phosphates, and sulfides are insoluble, and the hydroxides also insoluble, except, now here the exception is a very interesting exception. Let me see if I can get a different color here. So you have like sodium group 1A. Wait 1 second. I didn't like that color. Anyways, so sodium, potassium, ammonium. Wherever you have sodium, potassium, ammonium, and again, see this troublemaker, calcium came, barium came, strontium came. You see, barium, strontium, calcium all the time. So ammonium and potassium group. So generally, group 1A, we have ammonium. Group 1A is lithium, sodium, potassium, rubidium, cesium, francium, but more common ionic compounds are sodium and potassium ones. That's why they're here. Ammonium is also insoluble. Anytime it attaches to anything, ammonium will make things soluble. Group 1A elements, anytime they attach to any of the non-metals or polyatomic ions, soluble. And then similarly, we have the barium, strontium, calcium hydroxides. all the hydroxides are insoluble except all the group 1A, ammonium and barium, strontium, calcium hydroxides. Those will be partially soluble. Similarly, the sulfides of calcium sulfide is partially, soluble. Some exceptions are there. So refer to this table for the ionic compounds. Okay. Now let's look at the solubility of magnesium hydroxide. Is it soluble or not? So based from that table, soluble is insoluble or soluble. All hydroxides are insoluble, except, let's say magnesium. One second. What's the magnesium? Hydroxide. Yeah, magnesium hydroxide is not here, right? So that's why it is. So just refer to this table and you will get the answer. Solid. Potassium bromide. Potassium, group 1A. All group 1A are always going to be soluble. So every time, no matter what it is attaching to. So this is going to be aqueous. Okay, so some ways to recognize them. So all hydroxides are insoluble. So, that's the rule. Okay, lead nitrate. So here, what is the decisive factor is the nitrates. All nitrates are soluble. All nitrates are soluble. So when are you going to, now if this is soluble, aqueous. Okay, zinc nitrate, once again nitrate, soluble, so aqueous, right? And then lead bromide. Now this is lead. Remember that Castro bar and mol, L part of the mol is the lead. So let's check one again. Bromides. So let's look here. Chlorides, bromides, and iodides. And we do have lead iodide. We have lead bromide. Sparingly soluble or sparingly insoluble doesn't matter. It is still insoluble. So here, this is insoluble. So it is going to exist as a precipitate. PRECIPITATE. This is S. Next is strontium phosphate. Strontium phosphate, all the phosphates are insoluble, but double check, because strontium is that one of the troublemakers. So is it forming any exceptions? No. So all the phosphates are insoluble. So this would become insoluble. So this is S, solid. Okay. So this is the solid, insoluble part. Okay. All right, predict what will happen. Now here you have the solution, the aqueous solution of strontium hydroxide. So SR, strontium is group 2A. Okay, so this will have +2 charge. Okay, hydroxide is OH minus. So OH minus is -1 charge, is added to an aqueous solution of iron 2 chloride. So iron, so this iron 2 means +2 charge. How do you know it's +2 charge? From here, the charge. And chlorine is what? Chlorine is in group 7A. So the charge is, charge for the 2 A's is +2. 7A charge is -1. Okay, so this is the thing. Now, when these guys are in the aqueous solution, predict what will happen, whether a precipitate will form or not. So we would, because strontium hydroxide would be partially soluble, or is it not? Let me see. Hydroxide, yeah. Strontium hydroxide, sparingly soluble. So yeah, some reaction will occur. So strontium is going to outer, inner. Strontium is going to connect with chlorine, and iron is going to connect with hydroxide. So here, what are they forming? They are forming here, what is forming? So strontium in its +2 state, combining with chlorine -1 state. Excuse me. So what happens? Crisscross, this number comes here and this number comes here. So what do you get? You get SrCl2. The other one is what? Fe +2 state mixing with OH -1 state. Okay, so what is happening? Crisscross, this number comes here and this number goes here. So what do you get here? You get as FeOH whole twice. Okay, now whether you're going to form a precipitate or not. So strontium chloride and iron hydroxide. Just once again, go back and look into this table. Iron hydroxide. So remember, all hydroxides are insoluble except group 1A and barium strontium calcium. So that iron hydroxide is a solid. And the other is strontium chloride. Now, strontium chloride, all chlorides are chloride, bromide, iodides. All of them are soluble. Oh my God, excuse me. Soluble, but there are no exceptions. So we will see here that strontium chloride is aqueous. It is soluble in water, but iron hydroxide is insoluble. So this is the one that will form a solid. So formation of solid is going to be there in this reaction. Next is potassium, solid potassium phosphate is added to an aqueous solution of mercury 2 perchlorate. So let's write down potassium phosphate. So potassium is here, K, group 1A. So the charge is +1. And let me put this here a little bit. Potassium will have +1 charge. Phosphate, polyatomic ion, it has the standard -3 charge, which you should recognize, is added to an aqueous solution of mercury 2 perchlorate. So mercury 2. So this already tells you that mercury is in +2 state. Perchlorate is ClO4 -1, polyatomic ion. You need to recognize them, or they are listed in the handout and you can always cross-check. This number comes here and this number goes there. This number comes here and this number goes there. So this is how they will form the solids, right? But formulas. But we are going to now see their products. So when these are being reacted, so this is being reacted. So potassium is going to mix with perchlorate, okay? And mercury is going to mix with phosphate. So again, mercury is one of the troublemakers. So what do you get here? You get here potassium KClO4 plus, okay, Hg3PO4 whole twice, okay? Remember that Hg has +2 charge, PO4 -3. So crisscross when they mix. So this number comes here and this number comes here. So this makes it Hg3 brackets PO4 whole twice. All right. And then potassium with +1 charge and ClO4 -1 charge. So that is how they produce ClO4. So this is the potassium chlorate is like plus minus charge cancel out. So potassium, because it's a group 1A, this is group 1A. So this is going to make it, this is group 1A. All group 1As are going to make it soluble. So they are always soluble. So therefore, potassium chlorate is going to be soluble in water. So this is going to be AQ. But remember mercury, that mol, and then phosphate. So this is the one that is forming a solid. Okay. So solid. And then perchlorates, anytime perchlorate attaches to it. So in this state, when it is with mercury, perchlorate is soluble in water. That is why it's ionizing. And group potassium is group 1A. Okay. So this is definitely, all this is forming a solid. Okay. Next, sodium fluoride is added to the aqueous solution of ammonium formate. So here sodium, solid sodium fluoride. So sodium fluoride now is added to an aqueous solution of ammonium formate. Now, ammonium formate. Okay, so here, let's do this simple question. Whether, just before writing, let's say you don't know ammonium formate, and I'm not expecting that you know ammonium formate in the elementary, introductory chemistry class, because formate is organic molecule. But there's something else. Ammonium. Anytime ammonium attaches to anything, soluble. Anytime sodium attaches to anything, soluble. So as far as even though sodium is going to combine with formate, and then ammonium is going to combine with fluoride. So even in that case, sodium formate, ammonium fluoride are because sodium and ammonium are present. So even though they are on the reactant side, but even on the product side, on reactant and product side, both the times, in the reaction. Therefore, all aqueous. So no solid will be formed. No solid is formed in this reaction. Okay. Next is aqueous solutions of calcium bromide and cesium carbonate. Aqueous solution of calcium bromide. Aqueous solution of calcium bromide, CaBr2. You should know how to write the formulas, okay? And cesium carbonate, CeCS carbonate, CO3, okay? So here, double displacement reactions, basically. Calcium combines with the carbonate and cesium combines with bromine. Okay, so in that case, what do you get here? You get calcium carbonate and you're going to get cesium bromide. Now, cesium bromide, lithium, sodium, potassium, rubidium, cesium, francium. So this is a group 1A element. That is why there is only one bromine. Remember that. Calcium has +2 charge. It is a group 2A element. So therefore, +2 charge. So just so you remember your naming. So group 2A. So therefore, it will have +2 charge. Bromine, in this case, is -1. Why? Because it's a group 7A element. So it has a -1 charge. Cesium carbonate, cesium is in group 1A. Therefore, charge is +1. And carbonate is -2. Okay, so it's a standard polyatomic charge with -2. So this should be actually 2 here. Okay, the right formula. Yeah, that is why when we balance it, it will be 2 here. So 2, yeah, that way. Okay, then you have calcium, group 2A, +2 charge, and you have carbonate, -2 charge. So this way, these charges cancel out. You have cesium, which is group 1A, +1 charge, bromine, and bromine is 7A, -1 charge. So you see, that's why these how are these formulas formed? So this is CaBr2. Okay, this one is Ca2CO3. This one is CaCO3. +2 and -2 cancel out. And this one is CSBr, sorry, CSBr. All right, so this is the way, you identify. So now here, will the solid form or not? So remember, cesium this is group 1A. So group 1A will be soluble. So this guy will be, group 1As are always soluble. So this would be aqueous. Okay, calcium bromide and cesium carbonate. So here they are saying aqueous solutions of calcium bromide and cesium carbonate. So soluble, partially soluble also. Cesium group 1A is soluble, but carbonates, all the carbonates are insoluble. So this would be a solid. Okay. So this is a good practice of for the, identifying the solubility. Okay. Next is write the balanced net ionic equation. So here, once again, you are given potassium carbonate and strontium chloride. So what are we going to do? Here we are going to identify, first of all, the products. Okay. Then we are going to balance the molecular equation, balance the equations. Then we are going to ionize. And then we are going to create a net ionic equation, net ionic. And then in the net ionic, we are going to see which ones are the spectator ions. And we are going to remove them and we will have the final one. Okay. Now, all right, let's get started here. K2CO3 plus SrCl2. Okay, so what is this here? Here you have 2 potassiums reacting with chlorines, outer. And then we will have the strontium strontium with carbonate. Okay, so potassium with chlorine and strontium with carbonate are going to mix to form the outer, inner. Okay, but okay, potassium. So it's very important you know these first so that you get the right product here. So first of all, remember that the group numbers and the charges, that table I showed you earlier when the nomenclature was there. So refer to that. So charge. So potassium is in group 1A. Potassium is in group 1A and the charge is +1. And then the other carbonate is just a regular -2 charge. Okay. Strontium is in group 1A and the charge is +1. Chlorine is group 7A, so the charge is -1. Okay, so now the new substances that are formed, you're bringing potassium and chlorine. Potassium has -1 charge, +1 charge. Chlorine has -1 charge, so it cancels out. So this is going to give you KCl, simple. Oh, there's also products and solubility also. We have to identify the solubility. Very important. Okay, next is the KCl. And then you have strontium with carbonate. But remember, strontium is +1 charge and carbonate is -2 charge. So what we are doing here, we are going to, this number comes here and this number comes here. So what do we get here? We get SR2CO3. Okay, that is for the one we don't write. Okay, so here we have SR2CO3. Okay, so this is unbalanced yet. We only identified the products. So this is how you get the products, but the equation is still unbalanced. We haven't checked the balancing yet. Okay, next step is you're going to see the solubility. Okay, so let's write this again. K2CO3 plus SrCl2 gives you KCl plus SR2CO3. Okay, balancing. So we see here, there are 2 potassiums. There's only 1 potassium. So obviously that's not balanced. Carbonate is 1, which is fine. This is 2 SR2, this is 1 SR, and there are 2 chlorines here, there's 1 chlorine here. So pretty much, so what we do, before we write, I don't want to write because I don't have the space. So there are 2 potassiums on one side. If you put 2 here, this 2 applies to potassium, it applies to 2 chlorines. So there are 2 chlorines on one side, 2 chlorines on the other side, color coded, chlorines here and 2 chlorines here. And this thing balances. 2 potassiums and 2 potassiums balances. Okay. Now carbonates are 1 and 1, which is fine. But let's look at strontium. There are 2 strontiums on one side, but there is 1 strontium on the other side. So what are you going to do? If you put 2 here, this makes 2 strontiums, but then it makes 4. It makes 4 carbonates. Hold on. Okay, guys, sorry about that. I actually caught my error. And the error was strontium is in group 2A. I am so sorry. I think I was rushing or something. I'm very sorry. So please disregard everything that we said earlier. But now we are going to look at, so I was just trying to explain the writing of the formulas, which was, this is how the K2, this number comes here and this one goes here. So this gives you K2CO3. And then similarly, this number is going to come here and the one comes here. So this is SrCl2. Okay. And then when they switch places, this gives you not SR2. So this was a mistake here. I'm sorry. So when they switch places, when they give you the products, potassium combines with the chlorine. So potassium is 1, and potassium has 1 charge and chlorine has 1 charge. Okay, so that is why it's just written as KCl. But SrCl, sorry, I was thinking about cesium and I'm writing about, sorry about that. Okay, so strontium plus 2 charge reacts with the carbonate. Okay, and carbonate is minus 2 charge, so that cancels out. That is why it is SrCO3. SrCO3. Okay, so that's correct. Now this is our equation. The equation is K2CO3 plus SrCl2. This gives you KCl and SrCO3. Okay, so now we see here that there are 2 potassiums, 1 potassium. So if you put 2 here, this makes 2 chlorines also. Okay, so chlorines and potassiums got balanced. There is, yeah, so now this is all balanced. So there's 2 potassiums, 2 potassiums. There are, there's 1 carbonate, 1 carbonate. There is, sorry, there is, one second, let me get another color. There is 1 strontium. What is this? 1 strontium, 1 strontium and 1 strontium. And there are 2 chlorines, 2 chlorines. Let's do this one. 2 chlorines, and that 2 in coefficient of 2 applies to chlorines. Okay, so that's what it is. Next thing, we need to identify the solubility. Okay, so for the solubility, KCO3, remember group 1A, potassium is a group 1A. Therefore, this molecule is going to be soluble, or this compound is going to be soluble. Strontium chloride, all chloride. Now let's look, just double check. All chlorides are chlorides. All chlorides are soluble except, so here we don't see the halides, the solubility, so we don't see the strontium. Although strontium is one of the troublemakers, but it is soluble here, so aqueous. Okay, potassium chloride, again, it is a group 1A, aqueous. Then comes the strontium carbonate. Is it soluble or not? All carbonates are insoluble except group 1A and ammonium, and we don't see any other that is sparingly soluble or insoluble. So therefore, solid. All right, next is write the total ionic equation. So this is called a balanced molecular equation. Okay, now we are going to write the total ionic. So I don't have the space here. This is the total ionic equation. Total ionic equation. 2 potassiums, sorry, 2 potassiums plus 1 charge, aqueous, plus 1 carbonate minus 2 charge, aqueous, giving you 1 strontium plus 2 charge, aqueous, plus 2 chlorides minus 1 charge, aqueous, giving you 2 potassiums plus 1 charge, aqueous, right? And plus 2 chlorides minus 1 charge, aqueous, plus SrCO3. So this is a solid. Solids, make a note, do not ionize solids. Do not, never ionize solids. Okay. Now, so this is the total ionic equation. And now comes the net ionic. Net and ionic is, in total ionic, we obviously ionize everything. In net ionic, we only bring in the ions that are ions that show change of state. Okay, so the ones that are going from aqueous to solid, which ones are those? If you look at it here, that look at here, that potassium is aqueous on one side. Potassium is also aqueous on the other side, on the product side. All right, then look at the chlorides. 2 chlorides are aqueous on one side, 2 chlorides are aqueous on the other side. So which ones are showing the change of state? The ones that are showing the change of state is the strontium going from the aqueous to a solid side, and carbonate going from the aqueous to a solid side. So you're going to write that down here, that strontium Sr in +2 state, aqueous, and carbonate, CO -3, aqueous, right, is going to give you SrCO3, SrCO3 solid, and that is like, you know, in the solid state. So that is your answer. Okay, that is the answer. The total ionic equation. Ionic equation is the guys that show the change of state, they get, you know, put. So which ones are the spectator ions? Spectator ions are 2 chlorides ions and 2 potassium ions. Okay, all of them are aqueous in both the sides, reactants in the products. Okay, so that is your balancing the ionic and the net ionic equation. Okay, let me see if I can make this even smaller. All right. Okay, so that's deals with that. Next is here again, they are saying that because, you know, otherwise this video will become very long. So we will have to break it up into parts. Okay, so I'm going to stop here. And we're going to look at I'm going to leave this. You guys have to figure this one out yourself. It's the same thing as we did earlier. Neutralization reactions, and then the evolution of the gas, and then the assigning oxidation numbers, writing the equation for the decomposition. All this we will continue in the next video. Okay, so for now we will stop on this one.